Let me tell you a story. Did you know only 40% of software development projects meet schedule, budget, and quality goals? That's insane. We've been developing software since the 50s. If any other industry had that low a success rate or schedule rate, it'd be catastrophe. Imagine road work or building a house or almost any other industry or in the hospital. It'd be horrible. So how can we improve this rate? So a lot of software engineers do, and for a lot of companies and research, is they look into increasing this rate. And one of the ways to do this is to increase or improve your resource allocation during testing. Because according to Pareto-Zipf's types law, only about 20% of the code causes 80% of the faults. So what our research has done is hopefully help increase the ability to identify this 20%. I always like to start off with vocabulary terms that you'll see in the presentation. So they might be a little different than what everybody's using. So there's 4 of them for this presentation. The first one's static code metric. These are metrics which describe the size and design complexity of software. There's change metrics. These capture the change process that occurs to a file during development. There's the simple model. The simple model represents the decision tree being built just using the static code metrics. It's not necessarily simple. That's just a term we're using in the presentation, in the paper. The advanced model is a decision tree which uses the static code metrics plus 1 or more of the change metrics. Predicting fault-prone software is a major area of research for software engineering. Static code metrics have been successfully used to create software defect prediction models, and there's been a lot of research on this. We will be creating advanced fault prediction models using static code metrics and change metrics. There also has been plenty of research on change metrics, but not as much as static code metrics. Once we have those models done, we will then analyze the results to determine if the addition of the change metrics significantly improve the performance of the models. Now, how we're going to be doing this is all the static code metrics are going to be the independent variables because they won't be changed. They'll be in every single model. The change metrics will be our factors, and then our dependent variable will be the G score, which takes into account recall and false positives. That's kind of how we're going to measure our metric to measure the success. There has been a large amount of research on static code metrics and change metrics, which we've documented in our paper. But the two that were very similar to kind of what we were doing. Now, I'm going to apologize in advance for the pronunciation of these authors. I know I'm going to mess these up. But the 2 papers, the first one was titled, Which Process Metrics Can Significantly Improve Defect Prediction Models in Empirical Study, was written by Lech Medyski and Marian Dresko. The second one was called Applying Machine Learning to Predict Software Fault Proneness Using Change Metrics, Static Code Metrics, and a Combination of Them. This was written by Yasser Ali Asheri, Katrina Goseva Popstajanova, Dale Dzelski, and Thomas Devine. The first paper used a different success factor or success metric. We're using the G score. They used efficiency of their models. They also used a larger amount of data sets. And then the second one used 3 different classifiers, whereas we're just using the J48. They used 3 different ones. They did use the G score though as their metric to measure success. But they only use 3 data sets of 1 software package, whereas we're going to use 3 software packages and 11 data sets. We used 11 data sets from 3 separate software packages. 2 of them are open source, Ant and Xerxes. We used 4 different releases from Ant and 3 different releases from Xerxes. And then we also use a proprietary software from an insurance company, and we use 4 different releases of that. We did not create these data sets. They were used in the Medieski and Jezeko paper, and they're the ones that actually created the data sets. But they have been used in several research projects, and they are a trusted source of the data sets of data. Medieski also noted all product static code metrics were calculated with the OKGM tool 2, and the process / change metrics and the defect count were collected with a tool called bug info 3. Now we also did our own data audit for data quality and found the data quality very high. So the static code metrics we used are listed here. There's 21 of them, I believe. They were used in all of the models, the simple and the advanced. They've been used in several other research projects, and they've been proven to be good predictors of faults. Since our research was mainly concerned with the impact of chain metrics on defect prediction models, we will concentrate the data analysis on those metrics versus the static code metrics. The number of revisions metric is the number of revisions of a given Java class during development of the investigative release of a software system. The number of distinct committers is basically the number of distinct authors who committed their changes in a given Java class or worked on the class. The number of modified lines is the metric that calculates the sum of all the lines of source code which were added or removed in a given Java class during that release. The number of defects in previous versions calculates the number of defects repaired in a given class during the last release of the software. Slides 8 and 9 provide a data visualization of all our metrics, or the change metrics, sorry. So the first slide is the histograms. And you can see here that the data is highly skewed towards 0. This is after we did a logarithmic transformation of all the data. It was much more skewed from the initial values. We did do a logarithmic transformation using the natural log. This slide shows the scatter plots of the change metrics. After we performed the logarithmic transformation, the visualization, this visualization became a little more useful. You can kind of see there is some linear relation, or possibly a linear relation, between the change metrics and the defects. Since we are adding the change metrics to the models, we want to determine if the data we are adding is already represented in the simple defect prediction models. As you can see in slide 10 here, we compare the change metrics to the defects and see if there's any correlation between them. There's close to 70% correlation for the ANT project, and then various other projects. Because the data was not normal, we used the Spearman correlation to see if there's any relationship there. Slide 11 shows the Spearman correlation for comparing all the change metrics to the static code metrics. As you can see, there is hardly any correlation there. So this hopefully leads us to believe that the change metrics will be adding new information to the models, which is what we want. So to determine if our new advanced models significantly improve upon the simple models, there's 5 questions we will need to answer. What are the G-scores for the simple defect prediction models when using just the static code metrics? What are the G-scores for the advanced defect prediction models for each data set, including the static code metrics plus 1 of the change metrics? And then what are the G-scores for the advanced data prediction models for each data set, including the static code metrics plus all of the change metrics? And then once we find that information, then we can use that information to answer questions 4 and 5, which are: is there a significant increase in the G-score for any of the advanced defect prediction models using a single change metric? And then 5 is there a significant increase in a G-score for any of the advanced defect prediction models using all of the change metrics. So for the data preparation phase of our case study, what we did first was import the 11 data sets into a MySQL database. This allowed us to perform some simple data preparations using queries, SQL queries. We checked for empty values in all of the metrics. We checked for bad formatting in every metric column. So some of the things we found, there was actually some formatting errors that we found, and we were able to correct the data types so that when we did use Weka to generate the decision trees, it classified them correctly. One of the other things we found was for several of the change metrics, there was just a textual dash as the entry, the data entry. Now, usually that would mean that we don't really know what that means. It wasn't specified, but for some of them, some of the other data sets, if there was like an initial release, there was no data for these change metrics because there was no changes yet. So I double checked to make sure we double checked to make sure that this was not an initial release and they actually had data for that release. And then so instead of leaving it a dash, we reasoned that, or we concluded that it was meant to be 0, which is no information or no faults or no number of modified lines. That was 0. So we switched the dash to a 0, so that column then became numeric and could be used in Weka. So what we did then was we plotted the data on the histogram and scatter plots, and then we really discovered how skewed the data was. It was very skewed. So to reduce that skewness, we did a natural logarithmic transformation on the data using the natural log of n+1. That way, because there's a lot of zeros for the defects specifically. So that 0 would be a natural log of 1, because it's n+1. So that gives us a 0 again, which is kind of the value. And it did reduce some of the skewness, and it made some of the visualization a little bit easier to see. Once that was done, we then were able to hook the Weka and MySQL together and create all the data sets in the Weka format using SQL queries, and then save them and then use them. And then once that was done, we were ready to do our case study. So what we did is we used those 11 data sets, and I also included, so total we had 15 data sets, because I made a data set, because it was in MySQL, we were able to aggregate the various versions of software packages. So I took all the releases that we had, data sets releases, and I merged them into a software package data set, and I did that for all 3 of those. And then we merged all of the data into one large data set, and we also ran. So for each of those 15 data sets, we created a simple model and then 5 advanced models. So there was a total of 90 models that we created and tested and trained and tested on. So first we need to answer research questions 1, 2, and 3. And to do this, we use Weka's implementation of the C 4.5 decision tree algorithm, J 4.8, which uses information gain as a splitting factor for the decision tree. For the settings, we looked at doing optimized settings, but it really is not the purpose of the research. We really just want to see the improvement from using different types of metrics. So the settings we used were, there was a 0.25 confidence factor. We required at least 2 instances to make a leaf. And then we generated a binary tree versus an n-ary tree. To train, we tested the decision tree. We used to train and test. We used tenfold cross validation, which basically breaks up the data set into 10 different sections, trains on 9 and tests on 1, and iterates through so that all of them eventually are tested on all the folds. When preparing the data, we create a simple model using the static code metrics, and then we record the confusion matrix results. After that, we create the advanced model using the addition of the change metrics and record the confusion matrix result. Once we have the confusion matrix information generated, we correspondingly generate the recall, false positive rate, and the false alarm, and then rate, and then the G-score. So on this side, you can see how we kind of recorded the results of the testing and training of our decision trees. We did this for every single data set. And then we used, there are the formulas there for recall, false positive rate, and the G-score. And there's also a sample of our confusion matrix we used. And as you can see in that little table there, the confusion matrix is just also recorded there, and we use that to calculate the scores. Now, in the following two slides, we're going to have a little bit different data visualization for us. So as you can see on that table, and you'll see it on the next slide, what we did is we took all the data sets and all the results from running the training and testing, and we color coded them. So if it's green, it's a desirable result. If it's red, it's a not desirable result. If it's blue, it's neutral, nothing changed. So it's just kind of almost like a scatter plot, but different, just so you can kind of see, get a general idea of how the change metrics performed. And then the following slide is just a 3D bar chart or trend on the G-score of every data set, and test. So this is the results visualization. As you can see, we just kind of did this so it made it easier for us to see, is there a trend that we could see based on what the results are right away. And it looks like I have this, not just the G-score, but all of the things that we need to do to get the G-score. So the recall, the false alarm rate, and the G-score, all there for all the data sets and models. So it looks to me, just by visually looking at it, that there is an increase in desirable outputs once you add the change metrics. This does not include the base static code metric models. That would be what we're comparing them to, obviously. So this slide is also another form of data visualization for our results. So each 3D bar graph is a software package. It's kind of broken down. They're not in order, other than the left side is a static, what we're comparing it to, and then it kind of goes from the right. And then I just put the shorter, the lower magnitude releases up front. So you can see it's kind of all over the place. It's kind of tough to visualize a trend. It does look like overall there is an increase in G-score when you add the change metrics, but in some there's not. Like the ANT package, it's definitely not. It's no change at best. If more than likely it's worse. So we're going to have to use data analytics to prove any sort of significance. In order to answer research questions 4 and 5, we had proposed some hypotheses. So we proposed 5 of them. The nulls were basically the simple models that just included the static code metrics did not, when compared to the advanced models, their G-scores did not change. And then the alternative hypothesis is that the simple model's G-score was less than the advanced model G-score. So as you can see in slide 20, that's kind of how we reorganized the data. We broke it up so that this was all the static code metric data set, and there's 15 entries, basically, G-score entries. And then we did it for each of the change metrics and then for all of the change metrics. So here's the results of our statistical analysis. So how we got here is like I said, we reordered the data. So there's 50 entries of the initial read, which was the simple model, and then there was 15 entries of the advanced read for each of the advanced models. And so basically it was a paired test. We used first thing we did was we confirmed that the data was normally distributed. We used the chi-squared goodness of fit test. All of the G-scores, all the data for the G-scores was normally distributed. This allowed us to use a single-tailed paired t-test to confirm significance. Our significance factor was 0.05. So as you can see in the results, all of our results, the p-values were less than 0.05, which allows us to reject the null hypothesis. So there was no hypothesis, so there was no change. So that p-value means that there is change. Now, whether if it is it decrease or increase. So we can determine this by looking at the t-stat number. It is a negative number. That means that the advanced models number was greater than the simple models number. Or the g-scores were. So that indicates that there was an increase in the g-score, which is what we want. So that means an increase. There's a decrease in false alarms and an increase in the recall. Threats to validity. We have selected metrics which have been shown through previous work to be good predictors. We've had well-defined problem statements, variables, factors, and hypotheses, which have allowed our case study to test what we intended to. So we believe we've ensured construct validity. For internal validity, we did not acquire the metrics ourselves, so we did not generate the data sets ourselves. They're publicly available data sets. So there is a threat to internal validity as far as the data accuracy. But the data sets have been used in several related research case studies, and we feel the data quality is very, very high. We also confirmed there was no missing data. We performed a few data transformations to increase the quality of the data, so we feel the internal threats are very low. Conclusion validity. We believe our statistical analysis to be sound. We did not violate any assumptions like normality. We increased the number of data sets to increase the sample size and the power of our analysis. We do see a random heterogeneity of subjects as a conclusion threat to validity because of Prop 1 advanced models were affected more than the other software packages advanced models. The Prop 1 G-score increases could have skewed the outcome of our overall data analysis. So future work will include additional data sets to further increase the conclusion validity. For external validity, our case study includes 3 separate software packages. While this is more than most of the previous related work, it is really not large enough to generalize. So again, we cannot claim our finding to be generalized in all software packages without additional research. In conclusion, our main goal was to determine if simple models using only static code metrics created classifier models with higher G-scores and advanced models using static code metrics plus 1 or more change metrics. We also replicated the work performed by Medieski and also our professor, Katrina Kosova-Popstejanova. I'm sorry if I pronounced that incorrectly. In different ways, where we use less data sets than Medieski, and then we only provided one classifying algorithm versus our professors who used several or used 3. But we did use more data sets. Using J48 via Weka, we were able to build the simple models and advanced models and compare their G-scores. Using data analytics, we were able to prove with significance that the advanced models using both the static code metrics and the change metrics produced a higher G-score than models that were just used the static code metrics. Our future works would include performing the same case study on other data sets and thus increasing the power of our case study and adding more validity to it and making it more general. That would be it. Thank you very much.